Hey folks, we're into 7.2 similar polygons. All right. A blank is a transformation that enlarges or reduces a figure proportionately with respect to a center point and a scale factor. That would be a dilation. A dilation is a type of similarity transformation. A similarity transformation occurs when a figure and its image have the same blank, but not the same blank, have the same shape, but not the same size. All right, let's look at the picture together, shall we? We can see that there is a center of dilation, C, and we can see that there's LMP right here, and it's enlarged to form L prime, M prime, P prime. It's enlarged by some scale factor. Now, we don't know exactly what that scale factor is, but it's certainly enlarging LMP. So the scale factor must be, K must be greater than 1. Only a scale factor greater than 1 enlarges. All right, let's move on. Graph the image of each polygon with the given vertices after a dilation at the indicated center with the given scale factor. Okay, here's our given center of dilation, the origin, at 0, 0. And here is our scale factor, 1/3. In other words, what's going to happen to QRS? It's going to get smaller. Let's start by graphing QRS. QRS is right here. It's Q, R, S. Okay, I'm just going to freehand this. Okay, so we get something like this for QRS. Now, we want to get Q prime, we're going to get R prime, and S prime. How do we do that? Simple. As long as you are origin-centered, this is easy. You multiply 0, 6 by the scale factor 1/3. So 0 times 1/3 is 0. 6 times 1/3 is 2. -6 times 1/3 is -2. -3 times 1/3 is -1. And 6 times 1/3 is 2. -3 times 1/3 is -1. So we go over to 0, 2, -2, -1, and 2, -1. I'm just going to freehand this one. All right, and we have Q prime, R prime, S prime. What are some observations we can make? All right, if we start with QRS, Q prime, R prime, S prime is smaller. We had a reduction in size. Why? Because K is less than 1. Specifically, it's 1/3 the original perimeter. Each of the corresponding sides are 1/3 the size of the original. The perimeter is 1/3 the size of the original. All right, let's move along. Let's make some observations. You can pause here and make some observations on your own. You're going to be looking at these two triangles and making observations. These triangles are similar triangles. I go ahead and tell you that up front. What observations can you make about their 1, corresponding angles, 2, corresponding side lengths, 3, perimeters, and 4, areas? Why don't you pause it and give it some thought? All right. The corresponding angles here will all be congruent. So this guy right here, this guy right here is congruent to this guy right here. This guy is congruent to this guy. And this guy's got to be congruent to this guy. That is true for every pair of corresponding angles. How about the corresponding side lengths? They're not congruent. Clearly 3 is not congruent to 6. Can you see that? 3 is not congruent to 6. So we say that corresponding side lengths are proportional. This is important. The triangles are similar. The corresponding angles are congruent, and the corresponding side lengths are proportional. What do I mean by proportional? Well, this. 3 over 6 should equal 4 over 8, which should equal 5 over 10. So each of these equals 1/2. This 1/2 equals 1/2 equals 1/2. In other words, if I set up a ratio between the corresponding sides, here is a pair of corresponding sides, set up a ratio, a fraction, a ratio, I will get a common ratio. That means the sides, specifically the sides 3 and 6, are proportional. All right, how about the perimeters? What can we say about the perimeters? They will also be proportional. In fact, we could say that the corresponding side lengths are proportional with a scale factor of 2. Right, going from the small triangle to the big triangle, there's a scale factor of 2. 6 over 3 is equal to 2. Okay. Going from the big triangle to the small triangle with a scale factor of 1/2. The perimeter will also be proportional with a scale factor of 2. The area, however, will not work that way. Let's look at the area of the first triangle. The area of the first triangle is given by 1/2 base times height is equal to 1/2 base of 4, height of 3, which equals 6. Second triangle is 1/2 base of 8, height of 6, which equals 24. So it looks like the areas are proportional, right, with a scale factor of 4. So let's just say that right now, for now, the areas, the image is 4 times the pre-image instead of 2 times the pre-image. So areas really don't work in conjunction with side lengths and perimeters in direct lockstep. All right, let's read this together. 2 polygons are similar if and only if their corresponding angles are congruent and their corresponding side lengths are proportional. Once again, we say the polygons are proportional, their angles are congruent, and their side lengths are proportional. Okay, what do we mean when we say the angles are congruent? Look over here. You can clearly say A is congruent to W, B to X, C to Y, D to Z. So the angles are congruent. Next, we can say the side lengths are proportional. AB is 15, WX is 5, BC is 12, XY is 4, CD is 21, YZ is 7, DA is 18, ZW is 6. Now, what do you notice about each one of these factors? 3 equals 3 equals 3 equals 3. All of these proportions, all of these fractions, all these ratios are exactly the same, meaning the corresponding sides share a common scale factor. If you were going from the small triangle, the small polygon up to the big one, you'd be scaling up by a factor of 3. If you were going in the other direction, right? If you're going from the large polygon to the small triangle, you'd be scaling down by a factor of 1/3. Once again, in a similar polygon, the polygons are similar. Their corresponding angles are congruent, and their side lengths are proportional. If 2 polygons are similar, then their perimeters are proportional to the scale factor between them. All right, so if I added up A, B, C, and D, and I added up J, K, L, and M, they would still have the same scale factor between them than if I just looked at AB and JK. All right, so the perimeters, as we saw earlier, share the same scale factor as the corresponding sides. All right, example 2, use a similarity statement. Triangle FGH is similar to, and that's what this symbol means, JKL. JKL. List all pairs of congruent angles and write a proportion that relates the corresponding sides. The key to getting this right is following the angles. FGH. Let's go a single tick for F, a double tick for G, and a triple tick for H. Now it says that it's similar to triangle JKL. So a single tick for J, a double tick for K, and a triple tick for L. Now you can follow the congruent angles. The single tick angles are angle F. Okay, angle F is congruent to angle J. Okay, it's double tick angles. Angle G is congruent to angle K. And finally, angle H is congruent to angle L. It's all about following those angles, keeping them listed properly. How about the proportions? Well, FG, okay, FG is to, well, from F to G went from single tick to double tick angles. So from single tick to double tick angles, that's JK. And that all has to be proportional. Let's see, GH is proportional. It went from double tick to triple tick. So let's go from double tick to triple tick. That's KL. All right. And then lastly, we go from H to F. And that was from triple to single. So we're going to go from triple to single. LJ. See how following the angles will help us set up the ratios perfectly? Good. In the diagram, we're told that NPQR is similar to UVST. List all pairs of congruent angles and write a proportion that relates to corresponding sides. Why don't you try this on your own and then come back and we'll see how you did. All right, you're back. Did you follow the angles? NPQR. Single tick, double tick, triple tick, quadruple tick. Is similar to UVST. So start with U. UVST. Now if you do that, you'll not mess this up. If you try to go in alphabetical order, you'll mess up. All right, so let's write out all the corresponding angles. Angle N is congruent to angle U. They both have a single tick. Angle P is congruent to angle V. That's a double tick. Angle Q and angle S, because they have triple tick. And angle R and T have quadruple ticks. Follow the angles. That's the key here. How about the proportions? You're also going to follow the angles here. All right, NP runs from the single to the double. So what rings from the single to the double here? Looks like U to V. So NP is to UV. Okay, now we have PQ. That's from 2 to 3. That would be the same as VS. PQ is to VS. All right, now 3 to 4, QR, is to 3 to 4, ST. And finally, we've got RN, 4 to 1, following TU, 4 to 1. All right, again, the angles will save the day here. Let's look at example 3. Determine whether the triangles shown are similar. If so, write a similarity statement and a scale factor. Explain your reasoning. So here we want to fill in a little more detail than we have been in the past. We're given some numbers. Let's give this a shot. All right, angle N has a single tick, angle R has a single tick. So angle N is congruent to angle R. Angle Q and angle S have double ticks. And then by the third angle theorems, we're going to know that P is congruent to S. We'll put triple ticks there. Angle P. Angle P is congruent to angle T. All right, now we deal with the proportions. Let's see. Here we're trying to determine whether the triangles are similar. So we don't get to assume that their sides are proportional. We actually have to show that they are proportional. So that's a little bit of work that we have to do here. So let's do it. NQ is proportional to RS because we go from single to double ticks. And that's 12.5 over 10. See, 12.5 over 10. How many times is 2.5 going to 10? 4 times? How many times is 2.5 going to 12.5? 5. So that's equivalent to 5/4. Let's try the next one here. Double to triple is QP. QP is proportional to, see, QP is proportional to 2 to 3 ST. Let's see, QP at a length of 11.5. 11.5 over 9.2. That's also 5/4. If you're having trouble seeing that, you can just use a calculator for that guy. And then finally, we've got 3 to 1 is PN over 3 to 1, which is TR. Well, PN, we're told is 15. TR, we're told is 12. Right, if I divide by 3, I get 5. Divide by 3, I get 4. So you'll notice that we have a common ratio here. 5/4, 5/4, 5/4. If we set up the corresponding sides in proportion, in ratio, each of the ratios will be exactly the same, 5/4. So we have a common ratio or a scale factor. What's the similarity statement? Triangle NQP is similar to triangle RST. Notice single, double, triple, single, double, triple. Follow the names very precisely. How do I know that? Because, well, this stuff right here, that all the corresponding sides are proportional, and this stuff right here, all the corresponding angles are congruent. Now, what's the scale factor moving from RST, which is the small triangle, to NQP, which is the big triangle? All right, it's got to be a scale factor that's what? Greater than 1, or else you couldn't get big. Well, 5/4 is bigger than 1, so that's definitely our scale factor. What about this? A scale factor from NQP taking us to RST. Well, we're getting smaller, so your scale factor's got to be less than 1. So it can't be 5/4. It'll be the inverse. It'll be the reciprocal, which is 4/5. The reciprocal, which is 4/5. Slightly less than 1. All right. Let's look at example 3. You can try this one on your own. All right, photo editing. Kuma wants to use the rectangular photo shown as the background for her computer's desktop, but she needs to resize it. Determine whether the following rectangular images are similar. If so, write the similarity statement and scale factor. Well, how do you know if 2 images are similar? If the angles are congruent and the corresponding sides are proportional. Let's start with the angles. Well, you know what we can say? I mean, we have to show the following. We have to show this. That angle A is congruent to J, B to K, C to L, and D to M. Right? Can we show that these corresponding sides are all congruent? Angles are all congruent? Absolutely. Why? Because all angles are what? Right angles. Well, how did you assume that all the angles are right angles? It's right here. Rectangular photo. By definition, all the angles of a rectangular photo are right angles. Now let's look at the proportions. We know that, AB has to be proportional to JK. BC has to be proportional to KL. DC has to be proportional to ML, and AD is proportional to JM. Well, let's see. We've got 8 over 12 is to 10 over 15. Is that true? Is 8 over 12 equal to 10 over 15? Well, what's 8 over 12? 8 over 12. If I divide it by 4, I get 2 over 3. What if I take 10/15s and I divide by 5? What do I get? 2/3. So yeah, these are definitely proportional. All 4 pairs of sides are proportional. You're like, you only showed 2 pairs of sides. Yeah, but if CD is 8 inches, then AD is 8 inches. And if KL is 12 inches, then JM is 12 inches, right? Because these are rectangles. They have congruent sides, congruent opposite sides. All right, what's the similarity statement? Similarity statement is triangle. All right, so what's the similarity statement? Well, that quadrilateral ABCD is similar to quadrilateral JKLM because, well, this and that. What's this? All of the corresponding angles are congruent, and the second thing, all the corresponding sides are proportional. Okay, what's the scale factor from JKLM to ABCD? Well, we're going this way, aren't we? Going from big to small. So our scale factor must be less than 1. Well, good. We got the scale factor right here then. K is equal to 2/3. If you're like, I don't understand which way I'm supposed to go. Well, it says it right here. Scale factor from JKLM to ABCD. You can see you're shrinking, not enlarging, you're shrinking. Therefore, the scale factor has got to be less than 1. All right, what are we doing in example 4? It says use similar figures to find missing measures. So we know that these are similar figures. We just need to find the missing measures. ACDF. Angle A, angle C, angle D, angle F. First thing I do is I label the tick marks, right? VWYZ. Start with V, then W, then Y, then Z. If you don't do this, you're going to get the wrong sides. This helps get your orientation correct. Find X and Y. Well, let's see. We know that side CD has a length of 9. All right. What's the corresponding side to CD? CD went from 2 ticks to 3 ticks. So 2 ticks to 3 ticks is right here. It's YW. So that's 9 is to 6. As, well, let's see. We got this one right here is 12. 12, and that was from 1 to 4 ticks. So 1 to 4 ticks is right here. That's 3y minus 1. All right, so now if we have an equation of one variable, it's the variable y, and what we do is solve. We solve by cross multiplication. 9 times 3 minus y, 3y minus 1 is equal to 6 times 12. All right, no problems here. This is 27y minus 9, distribute, equals, well, 6 times 6 is 36. This must be 72. Bring the 9 to the other side, you get 27y is equal to 81. Therefore, y must equal 3. All right, we repeat the process. We know that 9 over 6, that was big triangle to small triangle, is, here we go, x is to 10. That means 6x equals 90, or x equals 15. All right. So we're asked to find x and y, and we did. Great. Next problem. Use similar figures and find the missing measures. All right, why don't you try this on your own and then come back. All right, let's see how you did. JLM. And we got QST. They're similar triangles. Well, let's just get our lengths correct. I'm going to mark L, the third angle here, with the triple ticks. I'll do that with S too, so it's hard for me to mess up. All right, we know that JM has a length of 4, and that's a single tick to a double tick. Therefore, single tick to a double tick is going to be QT, which has a length of 2. So 4 is to 2 as, now let's just try the next one. JL is 3y minus 2, and that's single to triple. Single to triple is 5. All right, so as long as you keep your corresponding sides correct, this should work out. We get 4 times 5 is 20. 2 times 3y minus 2 will be 6y minus 4. So you get 6y is equal to 24, or y is equal to 4. Y is equal to 4. Great. Now we can set the same kind of proportion. 4 is to 2 as 6x minus 3 is to 3. 6x minus 3 was 3 to 2. S to t was 3 to 2. Okay. 4 times 3 is 12. 2 times 6x, 12x. Negative 3 times 2, negative 6. Let's bring that 6 to the other side. You get 18 equals 12x, or x is equal to 18 twelfths. 18 twelfths divided by 2, you get 9 over 6. Divide by 3 from there, you get 3 over 2. Okay, so x is equal to 3 halves. Y is equal to 4. Great. All right, this problem is only for honors, so feel free to skip it if you're in standard. Show that JKLM is similar to PQRS by a composition of similarity and rigid transformations. So the similarity transformation is most likely going to be a dilation. It's the only one you know. And a rigid transformation here, I think, is most likely going to be a translation. State the specific transformations and show them on the coordinate plane. All right, let's make sure we know what's going on here. Let's get some locations. Let's do this very carefully. J is at the location 12, 8. K is at the location 16, 8. And L is at the location 18, 4. M is at the location 10, 4. All right. We want to scale this down. So we want to get to J prime, K prime, L prime, M prime. Remember how I did that? First of all, we have to know how much we need to scale this thing by. Well, look over here. JK has a length of 4, right? From 16 to 12 is a length of 4. And PQ has a length of 2. From 4 to 2, it's a length of 2. So it looks like the scale factor going from the large trapezoid to the small trapezoid is a scale factor of 1/2. So since this is origin centered dilation, what can we do? We can just half the numbers 12 and 8. So you get 6 and 4. Half of 16 and 8 is 8 and 4. 9 and 2. And 5 and 2. So let's graph these, shall we? 6, 4 seems to be right here. 8, 4 is right here. 9, 2 is right here. And 5, 2 is right here. All right. So look at it. Do you see a trapezoid? You do. Does it look similar to JKLM? Yeah, it does. Does it look like the perimeter's half the size? Yeah, it does. Let's just double check. What's the perimeter here? What was the length of this base? 2, 4, 6, 8. So the length of the base here, 1, 2, 3, 4. That's half. All right, I think we did a good job creating J prime, K prime, L prime, M prime. Now, all we have to do is move or translate J prime, K prime, L prime, M prime to P, Q, R, S. How do we do that? Do you remember? All right, let's think about this. If we want J prime to get to P, if we want J prime to get to P, what kind of translation vector do I need? I need a translation vector that's going to take me 4 to the left and then down 2. So here's their translation vector, -4, -2. Let's see if that holds for M getting to S. Well, where's M? M prime is at 5, 2. M prime's at 5, 2. Where's S? S is at 1, 0. Here, let's write that. M prime is at 5, 2. We needed to get to S, which is at 1, 0. So how much do you have to subtract from 5 to get 1? -4. How much do you have to subtract from 2 to get to 0? -2. So clearly our translation vector is correct. Translation vector, -4, -2. Notice these symbols right here. These are triangular symbols. That's what indicates the translation vector. All right. So what again did we do? We dilated JKLM by a factor of 1/2, and then we used a translation vector to use J prime, K prime, L prime, M prime to P, Q, S, R. So let's just write that down. We apply dilation of K equals 1/2 to JKLM. And I'll just write here origin centered. The dilation is origin centered. Okay? Once we've done that, we apply a translation of, let's see, -4, -2 to J prime, K prime, L prime, M prime. And that takes us to PQRS. All right, folks, that's really all there is to this. But let me just ask you these couple questions, see if you can answer them. When you're dealing with similar triangles, what can you say about the corresponding angles? They're congruent. And what can you say about the corresponding sides? They're proportional. And what do we say about the triangles? They are similar. That's the big idea here, folks. Enjoy dilations.